Okay, so we have this ring network that consists of 1, 2, 3, 4, 5, 6, 7, 8 links, and each link fails independently with probability q, and so the chance that a link will not fail is 1 minus q. So q equal probability of failure and 1 minus q is the probability of not failing. For any given link. Now, since this terminal transmits the packets in both directions, from A to B this way and from A to B that way, and because both directions are disjoint or mutually exclusive, the probability of transmitting the packet from A to B is the sum of the probabilities for each direction. Okay, let's call this direction 1 and this direction 2. So the probability of transmitting from A to B using direction 1 is 1 minus q, so that's the probability of not failing, raised to the power 1, 2, 3, 4, 5. Right? You have to pass the first link and pass the second and pass the third and pass the fourth and pass the fifth if you want to reach B, right? So this is 1 minus q to the power 5. But if you use the other way, direction 2, you have 1, 2, 3 links, and so the probability of successfully transmitting the packet from A to B in that direction is 1 minus q to the power 3. Okay, that's in direction 2. Again, because the two events, the two directions are mutually exclusive, the total probability is the sum a person has the disease or doesn't. I'm calling D having the disease and D bar not having the disease. Okay, let's write here D equal disease and D bar disease free. What is the chance of having the disease? The probability of having the disease. The prevalence of the disease, as they call it. It's 0.001. And therefore, the probability of not having the disease is 1 minus 0.001, which is 0.99999. If a person has the disease, two things can happen. The person can test positive for the disease or test negative, right? So you can test positive or negative. And if you don't have the disease, you can also test positive or negative for the disease. Test positive or negative. Now, if you do have the disease, what is the chance? What is the probability of testing positive? If you have the disease, the test will show that you have it with probability 1. There's a 100% of chance that the test will tell you that you do have the disease if indeed you have the disease. This conditional probability equal 1, and the chance that you will test negative if you do have the disease is 0, right? Because these probabilities should add up to 1. So this is 1, this has to be 0. Now, what if you don't have the disease? Well, if you don't have the disease and you test positive, it's called a false positive. Because you don't have the disease and the test is saying you do have it. It's wrong. The test is wrong. It's a false positive. And if you do have the disease and the test says no, negative, this is called a false negative. Right? We are told that the false positive rate is 0.005. 0.005. 1 minus 0.005 is 0.995. So this is 0.995. And the question is the following. Given that you test positive for the disease, what is the probability that you actually have it? So what's the probability that you have the disease if given, right, it's a condition, that you test positive? So what's this conditional probability? The definition of the conditional probability of A given B is the probability of A intersection B over the probability of B, right? P of A and B over P of B. So this equals the probability of disease and test positive over probability of testing positive. Now if you look at the tree, disease and testing positive, that's 0.001 times 1, right? It's a multiplication because it's AND. So this is 0.001 times 1 divided by the probability of testing positive. There are two ways of testing positive. You can test positive when you have the disease, and you can test positive when you don't have the disease. And the theorem says P of T plus is P of T plus and D plus P of T plus and D bar. It's the sum of the probability of the conjunction of D and T plus and D bar and T plus, right? Probability of T plus is probability of D intersection T plus probability of D D bar and T plus. Theorem of total probability. The probability of D and T plus is 0.001 times 1 plus the probability of D bar intersection T plus is 0.999 times 0.005. So 0.999 times 0.005. 0.1668. Let's say 0.17. So about 17% of chance that if you test positive for the disease, you actually have it, right? 17% of the time, when a person tests positive for a disease, that person will actually have the disease. We have a random variable x. We know the mean of x is 3. That's the expected value of x. And the variance of x is 5. We want to find the expected value and the variance of y. The mean and the variance of y. Okay, the mean of y is the expected value of 3x minus 2. Now recall that expected of ax plus b is a expected of x plus b, where a and b are constants, right? So this is 3 expected of x minus 2 of 3 times 3 minus 2, 9 minus 2, that's 7. Now, for the variance of y, the variance of ax plus b is a squared times the variance of x. Because b is a constant, the variance of a constant is 0. A is 3, so that's 3 squared times the variance of x. 9 times 5, which is 45. Okay. What is the standard deviation of y? So the mean of y is 7 and the variance of y is 45. The standard deviation of y is the square root of the variance of y, that is the square root of 45. We have a normal distribution with mean 1 and variance 4. Now, if the variance is 4, the standard deviation is the square root of 4. Sigma is square root of 4, which is 2. And the mean, the expected value of x is 1. What is the probability that x is greater than or equal to 1? Recall z is x minus mean over sigma, standard deviation. So let's make the change from x to z. Greater than 1 minus mu, but mu is 1, over sigma, which is 2. Uh, 1 minus 1 over 2 equals 0. Look at the Q table for the value 0, right? So this is Q of 0, which is 0.5. Okay. Now, the probability that x is less than 0, again, we make the change from x to z. We do 0 minus the mean, 1, over the standard deviation 2. That's probability that z is less than minus 0.5. And this is equal to 1 minus q of minus 0.5. Because it's less, you do 1 minus. Now, absolute of x bigger than 4. This is 1 minus probability that absolute of x is less than 4, and 1 minus probability that x is between negative 4 and 4. Right, negative 4 and 4. This is 1 minus probability that negative 4 minus 1, that's negative 5, divided by 2, that's 2.5, and 4 minus 1, that's 3, divided by 2, that's 1.5. And this is 1 minus the Q table value for negative 2.5 minus the Q value for 1.5. Okay, so this is Q of negative 2.5 minus Q of 1.5. The PDF of x is C e minus 3x and 0 otherwise. Let's find the value of c. We know the integral from minus infinity to infinity of the PDF is 1. We can break this integral into the sum of two integrals from negative infinity to 0 plus 0 to infinity. From 0 to infinity, the PDF is ce minus 3x dx. From minus infinity to 0, it's 0. Right? So this is 0. And and this is supposed to be equal to 1. Okay, c is a constant, so we can move the constant out. And this is c, 1 over negative 3 e minus 3x from 0 to infinity, and that's equal 1. Let's see, e to the negative infinity is 0 minus 1 over minus 3 e to the power 0 equal 1. 1/3 times c equal 1, c equal 3. This is the integral from x plus a to infinity of PDF dx. X is greater than 0, a is greater than 0, so x plus a is positive. So we have the integral from x plus a to infinity. The PDF is 3 e minus 3x dx. This e to negative 3 x plus a. Just do the math. Remember the CDF of an exponential distribution, because this is exponential. It's 1 minus e minus lambda. Here lambda equal 3 x. 1 minus e minus 3x. And so this is 1 minus this, which is 1 minus the CDF at x plus a. That's 1 minus, bracket 1 minus, so the 1's cancel. Minus and minus is plus, and you get e to negative 3. You change x into x plus a. And that's what we predicted. And C, what's the probability of x greater than or equal to x plus a, given that x is greater than or equal to a? Now, this is a conditional probability, right? P of a given b is P of a and b over P of b. This is b and this is a. The intersection of a and b, right? X is greater than or equal to x plus a and x is greater than or equal to a. This is a and this is x plus a. X greater than or equal to a and x greater than or equal to x plus a. See, so this is the intersection. Right? So this is equal to this divided by P of b, that is P of x greater than or equal to a. This is equal to e to the negative 3 x plus a divided by e to the negative 3a. E to the negative 3x, because the negative 3a's cancel. This is question 5. Something like this. So the area of one chip is 1 centimeter squared. The average number of defects on that chip is 1. So on average, one defect occur on a centimeter square of chip? And see, this is a question where we're only given a rate, an average, a mean, right? That's the only piece of data we have. That kind of question usually deals with Poisson distribution. La loi de Poisson. We have a hint right from the question. What is the chance that a randomly selected chip from the fabrication line chip will have no flaw? Let x equal the number of defects or flaws on a given chip, right? So you randomly select a chip, the area is 1 centimeter squared, and you ask yourself how many defects, how many flaws can be found on that chip. What is the probability that 0 defects, 0 flaws occur on that chip? So what we want is the probability that x equal 0. No flaws. We're using Poisson distribution, and the formula for the PMF of a Poisson distribution is exponential of minus mu times mu to the power x over x factorial. So this is going to be e to the minus 1 times mu 1 to the power x, x equals 0 over 0 factorial. So there is about 37% of chance that if we randomly select a chip from the fabrication line, we won't find any flaws, like a perfect chip. Just multiply the probability by the cost and you have the average cost. Now we have a new kind of chip where there is built-in redundancy, so that any single flaw on the chip can be repaired. Interesting. The chip area has been increased by 10%, and the new cost of producing a chip is $12. It used to be $10, it's now $12. You increase the size by 10%. It used to be 1 centimeter squared of area. The new area is 1 centimeter squared plus 10% of 1 centimeter squared. Okay, 10% of 1, and that's 1.1 centimeter squared. That's the new area for the new circuit chip. The probability that the chip will function is the probability that the number x, it's a random variable, the number x of defects is less than or equal to 1. No flaws, fine. 1 flaw, no problem, because any single flaw on the chip can be repaired. This is the probability that x equals 0 plus the probability that x equals 1, which is e minus. So we have to be very careful here. The new area is 1.1 centimeter squared, right? But this average is for 1 centimeter squared. So we need to compute the average number of defects on the new chip. We have 1 defect per centimeter squared. Let's say for 1 centimeter squared. Now for 1.1 centimeter squared, how many defects should we expect? What is the average? What is the mean? What is the expected number of defects on a 1.1 centimeter squared? cross multiplication. So we have 1.1 times 1.1 to the power 0 over 0 factorial plus e 1.1 to the power 1 over 1 factorial. Okay, so we're looking at question 6. Now, if you recall, the definition of the CDF it's the integral from minus infinity to x f of x dx. And here we need to look at three cases depending on the range of values of x. See, x can be less than 1, x can be between 1 and 2, or x can be greater than 2, right? So we need to look at each case. So let's look at case 1, where x is less than 1. When x is less than 1, the PDF f of x equals 0. And so the CDF, big f of x, the integral of 0 dx. Now, case 2, when x is between 1 and 2, we know little f of x equals 3 over 7 x squared. So big f of x is the integral from minus infinity to x, I'm just applying the definition, of f of x dx, which is the integral from minus infinity to 1 f of x dx plus the integral from 1 to x fx dx, right? The integral from minus infinity to x is the integral from minus infinity to 1 plus the integral from 1 to x. From minus infinity to 1, right, when x is less than 1, we know the PDF is 0, right? So this integral is 0 plus the integral from 1 to x of 3 over 7 x squared dx. And this is a very basic integral. The integral of x squared is x cubed over 3 from 1 to x. The 3's cancel out. And this is x cubed over 7 minus 1 over 7, right? X cubed over 7 minus 1 over 7. And case 3, when x is greater than 2, we know the PDF is 0, and so the CDF, which is the integral from minus infinity to x PDF dx, is equal to the integral from minus infinity to 1 plus the integral from 1 to 2 plus the integral from 2 to x dx. Now, from negative infinity to 1, the PDF is 0, and when x is greater than 2, the PDF is also 0, and between 1 and 2, it's 3 over 7 x squared dx. And so this is 0 plus 3 over 7 x cubed over 3 from 1 to 2 plus 0. This is 8 over 7 minus 1 over 7. That's 7 over 7. That's 1. Right? And so the CDF is when x is less than 1, big F is 0. When x is between 1 and 2, it's x cubed over 7 minus 1 over 7. And when x is greater than 2, it's 1. Next, we want to find the mean. That's the expected value of x and the variance of x. So let's find the mean of x. Now, the expected value of x is defined as the integral from negative infinity to infinity of x PDF of x dx. Right? That's the definition of the mean of x. And this is equal to negative infinity to 1 plus 1 to 2 plus 2 to infinity. Right? Now, from negative infinity to 1, the PDF is 0. From 2 to infinity, the PDF is 0. And so this is 0 and this is 0. And thus the expected value of x is the integral from 1 to 2 x times 3 over 7 x squared dx. Right? And this is 3 over 7 integral of x cubed. That's x4 over 4 from 1 to 2. And this is equal 3 over 7 2 to the power 4 over 4 minus 1 to the power 4 over 4. And this is 45 over 28. Now, the definition of the variance, sigma squared, is the expected value of x squared minus the square of the expected value of x. We already know the expected value of x. That's 45 over 28. And so we need to find the expected value of x squared and do the difference between this and that. Now, the expected value of x squared is the integral from negative infinity to infinity of x squared times PDF dx. And again, this is the integral from negative infinity to 1 plus the integral from 1 to 2 of x squared 3 over 7 x squared dx plus the integral from 2 to infinity, but those two integral equal 0, so I won't even bother. And this is 3 over 7. Integral of x4 is x5 over 5 from 1 to 2. That's 3 over 7. 2 to the power 5 over 5 minus 1 to the power 5 over 5. That's 93 over 35. And so the variance of x is 93 over 35 minus the expected value of x squared, right? So 45 over 28 squared. And this is about 0.074, something like that. To find the PDF of y, let's first find the CDF of y. Okay, let's find the CDF. And once we have the CDF, we'll take the derivative and get the PDF. The CDF, capital Y is x cubed plus 1. So this is the probability that x cubed plus 1 is less than or equal to y. And this is also equal to the probability that x cubed is less than or equal to y minus 1. Right? You move the plus 1 to the right hand side. By taking the cubic root on both sides, or simply raising both sides to the power 1/3, right? X cubed to the power 1/3 is x, and y minus 1 to the power 1/3 is y minus 1 to the power 1/3, or cubic root of y minus 1. So x cubed to the power 1/3 becomes x, and this is cubic root of y minus 1. And by the very definition of the CDF, this is also equal to the CDF of x, because we're dealing with x, at cubic root of y minus 1. The probability that x is less than or equal to cubic root of y minus 1 is precisely the CDF of x at cubic root of y minus 1. And what is this equal to? Well, we have to look at, we have to go back to the CDF of x. Big F of x is a piecewise function. It's 0 when x is less than 1. It's 1/7 x cubed minus 1 when x is between 1 and 2. And it's 1 when x is greater than 2. So CDF of y is also a piecewise function. It's going to be 0 when cubic root of y minus 1, you see, this is like x, but x is supposed to be less than 1. So cubic root of y minus 1 is less than 1. That's the first part. The second part says 1/7 x cubed minus 1 between 1 and 2. So this is 1/7 x cubed, but x is cubic root of y minus 1. So x cubed is cubic root of y minus 1 cube, right, cube, minus 1. And that's when this is between 1 and 2. When cubic root of y minus 1 is between 1 and 2. It's 1 when x is greater than 2. So this is 1 when cubic root of y minus 1 is bigger than 2. Now let's see. Cubic root of y minus 1 less than 1. This less than 1, if you raise both sides, you get y minus 1 is less than 1 to the power 1/3 is 1. If you move the negative 1 to the right hand side, you get y less than 2. This is the same as saying y is less than 2. Right? Okay. I'm going to write here. So this is when y is less than 2. You raise both sides to the power 3 to get rid of the 1/3, right? You raise it to the power 3. You get y minus 1 greater than 2 to the power 3 is 8. And you move the negative 1 to the right hand side to get 8 plus 1, that's 9. So this statement is the same as saying y is greater than 9. Okay? So this is y bigger than 9, which means the term in the middle cubic root of y minus 1 between 1 and 2 entails that y is between 2 and 9. Y is between 2 and 9. Y is between 2 and 9. The cubic root of y minus 1 raised to the power 3 is y minus 1, right? This is y minus 1, minus 1 again, that's y minus 2. That's y minus 2. So this is y minus 1 minus 1, y minus 2. And this is true when y is between 2 and 9. And this is the CDF of y. The PDF is the derivative of this function. The derivative. PDF of y is the derivative of the CDF. Between 2 and 9, the derivative is 1 over 7. Right, so that's when y is between 2 and 9. And otherwise, that is when y is less than 2 or greater than 9, the derivative is 0, because big F is a constant. So this is 0 otherwise, or else. By the way, this is the PDF of a uniform distribution over the interval 2 to 9. So y has a uniform distribution over the range